Okay, so last time we finished pretty much displacement-based solutions. I mean, it's not about finishing it. It's just to give you a sort of picture about or a taste of how these methods work, right? So there are many, many different problems. And this time we're going to move to stress-based solutions. So that's an entirely different approach. But before I do that, let me just mention one thing that eventually, in some sense, works for both displacement and stress-based solutions. And to highlight that point, let me just mention a problem, which is the combined tension torsion of a circular cylinder. I'm not really going to solve the problem once again because it turns out there's no need to. But let me just make a point and then move on. So suppose, remember this problem we considered at the very beginning of the displacement-based solutions to highlight, right, to sort of demonstrate how the method works in a context that we are very familiar with. So we had a cylinder. We had displacement prescribed to 0 at the left hand at z equals 0. So that was for us the z-axis. Okay, and additionally, we had no body force, and we omitted accelerations. Okay, so that was a problem that we were trying to solve, and we solved two different kinds of problems. One for a torque, that's the torsion, and then for the tension, where we apply a normal force P. In both cases, we eventually analyze the problem. Now, suppose we wanted to solve the problem for the combined scenario where the torsion and tension is, they are both simultaneously present. So then I can look at the problem, and based on our usual assumptions, let's say omitting end effects, etc., well, I can see that there's going to be some radial displacement, and that radial displacement is going to depend only on the radius. Due to the symmetry of the problem, there is no dependence on angular position in all cases. There is going to be a tangential motion, of course, due to the torque. It's going to depend on the axial position and the radial position. And there is going to be some elongation, and that's going to be a function of the axial position due to the application of the force. So again, all of those assumptions are based on our understanding of the behavior of an isotropic linear elastic material. So now, if I would like to find that solution, I don't need to go from scratch, right? So what I can do is I can remember that there's something called the principle of superposition, which we applied numerous times in ME 231 and ME 232, right? So in this case, the way the principle of superposition applies is essentially by observing that, well, I already solved two problems. For these two problems, I obtained two solutions. So for instance, for the tension problem, concerns the radial and the axial parts of the displacement, and the angular displacement, the tangential component u theta, is associated with eventually the torsion component. So that has to do with P, and this one has to do with the torque. Okay. And so I have essentially, let me write that with a different color just to highlight. So essentially the principle of superposition, the way it would apply and what it would eventually imply is that the solution is a sum of two parts. One that has to do with the pure tension problem, and the other one that has to do with the pure torsion problem, right? And from this, right, we follow a displacement-based approach. So first we propose a form for the displacement. We calculate the strain. So the strain is going to be a sum of the strains for the tensile and the torsion problems. And then we move on to the stress. Stress, therefore, is going to be a sum of the tension and the torsion parts. And now we invoke equilibrium, right? And before I invoke equilibrium, I remember that, right, these two individual solutions are such that these two individual stresses under these conditions are both divergence free. So divergence of sigma p is equal to 0, and divergence of sigma t is equal to 0. So this being the proposal for the form of the stress, so now what I need to satisfy is divergence of stress is equal to 0. This needs to be satisfied, but that is identically satisfied because that's equal to divergence of sigma p plus divergence of sigma t, which are individually satisfied by the individual solutions of the two problems, right? So this is therefore guaranteed, which means that you don't need to solve this problem once again. So we have solved a limited set of problems, but in principle, you can sort of combine these two into new problems, and you really don't need to solve anything all over again. And in fact, perhaps in some clever fashion, you can even construct or help solve different problems, one of which, it's a quite challenging one eventually, you're going to consider in upcoming homeworks. It's a plate with a hole. You'll pull on it, and there's a stress concentration effect eventually that you can observe. But the solution of that problem is not a particularly simple one. Okay, so it's a problem that looks like this. Right? Plate with a hole. We're going to pull on it. There is no obvious symmetry to the problem, but under certain assumptions and by also making use of the principle of superposition, you will be able to solve such a seemingly quite hard problem, but in the homework, not in lecture. Okay, so with that, I'd like to conclude sort of the displacement-based solution. So again, this is not necessarily something that pertains only to a displacement-based approach. It's just in the context of linear elasticity, it always applies, right? But my specific example is based on that displacement-based approach example. So now let us move on to stress-based solutions, right? Now this is an entirely different approach. If you like, it's just a different taste of solving these problems. But of course, it has its advantages. Both displacement-based solutions and stress-based solutions have their advantages and disadvantages. So in particular, the displacement-based approach is very methodological. You make some observations, and then the procedure sort of takes you through the solution. So for instance, remember that there we first, again, begin with the form of the displacement, and then we calculated the strain, right? And then, of course, we have the stress, and we linked stress to strain through isotropic linear elasticity. And finally, we invoked equilibrium. And once you start with the displacement, go through this loop, and eventually close it with equilibrium, you started with a proposal for the form of the displacement. This is your proposal. You observe certain symmetries, and you simplify the possible solution. But the possible solution is still very general. For instance, in this case, we have some function of r and z. We don't know what that function is. So we are starting here nevertheless. It's a rather simplified form. But once we close the loop, we know exactly what that function has to be. After also, of course, we impose the boundary conditions. Now, it's very methodological, but it can be a little bit painful. Now, it's not that stress-based solution is any easier, but in some cases, it can be easier. It can be more straightforward. And it will also help us solve problems where there is no obvious cylindrical or spherical symmetry, and working in the Cartesian coordinates in a displacement-based approach could be somewhat more harder. So in such a case, stress-based solutions will help us, and we will see how it helps us, and we will also see some of the tricks involved or some of the difficulties involved. So in this case, what we are going to do is entirely different. I'm not going to start here. I'm going to start here. Okay? I will start by proposing a form for the stress. Okay? Now, from the stress, then I will go and calculate the strain. All right? But, of course, I already know that any proposal for the form of the stress, I can always invert this relationship to calculate the strain, right? So let me remind you, if I had given you the stress, then the strain is 3 Poisson ratio over E, sigma H, hydrostatic stress plus identity, plus 1 plus nu over E, sigma. So given sigma, I can calculate epsilon, but not every form of epsilon, or in other words, not every form of stress is a reasonable stress, because eventually I need to make sure that the resulting strain field is indeed associated with some physical displacement field, and that is ensured by compatibility, right? But does my stress through the strain satisfy compatibility? So that's something eventually that I will enforce. Okay, so in the displacement-based approach, I start with a form for U. It's a very general form. Eventually, the constraint on that is imposed by equilibrium. In this case, I will start with a relatively general form for stress. And in this case, the constraint on that will be enforced through compatibility. Okay, so that's the different approach. Now, there's one more thing, obviously. So I start with stress through the strain. If I enforce compatibility, I know that there's a displacement field. I'll be able to solve my problem. In other words, the particular form for the stress. Just like here, I solve for the particular form of, let's say, U theta. Right? I propose the form. I want to solve for it. I will be able to solve for it. But what happened to equilibrium? Equilibrium is never in the loop anymore, because I start here. Once I enforce compatibility, I know that there's a displacement field. And in fact, I will be able to solve for it. But my loop is not a full loop. It finishes here. So it turns out that in this approach, when I start with the stress, from the outset, from the start, I need to ensure that this is satisfied. And that is one quite difficult part, actually, with the stress-based approach. I need to make sure that equilibrium is satisfied from the outset. That's a critical point. So this must be. Now, from the outset, in the technical literature, you will often see this wording. From the outset is, in Latin, a priori. Okay? Okay, so must be a priori, from the outset satisfied. All right, so let's see how that works out, right? So to summarize, I start with sigma, and I solve eventually a PD for stress. Now you will see that when I solve, what I mean by the stress is not directly sigma, but something else that delivers sigma. We'll see what it is. If not this lecture, next time. And once I've solved for a PD for the stress, which essentially appears due to the compatibility constraint, I'm essentially done. I have the stress after I also impose the boundary conditions. And if necessary, I can calculate the displacement. Since I'm enforcing compatibility, I know that there is a displacement field, but I may not need it. It's not a displacement-based approach. My solution delivers stress, not displacement. But if necessary, I can calculate it. So construct U if necessary. So that's the idea. Okay? And I hope the diagram sort of demonstrates that it is quite different. So now this stress-based approach works in is proposed for two-dimensional problems, intrinsically two-dimensional problems. So the problem itself could be 3D. All problems are 3D. But intrinsically 2D, remember, means it's either plane stress or plane strain. Okay? So since it's sort of limited to those two settings, what I would like to now spend some time and review and show is that irrespective of whether the problem is plane stress or plane strain, sort of the methodology is exactly the same. In fact, the equations are remarkably the same. There will appear only a single constant almost that distinguishes whether the problem is plane stress or plane strain. So I'd like to sort of work out the two cases of plane strain and plane stress to show how they are cast in a, let's say, a unified setting, a almost entirely identical setting. Okay, so I'm going to follow, I think, a few boards. The left-hand side of the board will always be plane strain. Right-hand side will also always be plane stress. And if I write something in the middle, it means it's sort of shared by both of them. Okay, so I'll try to emphasize that. But let me just make sure that this is, let's say, recorded in our notes. We are going to follow intrinsically 2D problems. So that's plane stress or strain. So I'm going to assume it could be any one of the directions. And it doesn't even need to be Cartesian coordinates, but I'm going to, in this construction, I'm going to assume Cartesian coordinates, although, again, the results are irrespective of the coordinate system. I will assume Cartesian coordinates, and I'm going to omit variations along the x3 direction. Okay, so just for the sake of discussion. So omit variations along x3. Okay, so the remaining directions, therefore, are going to be denoted with alpha, which could be 1 or 2. Okay? So instead of using I, remember I used to write, let's say, xi for the components of the position. Xi goes from 1 to 3. In this case, I will eventually write x alpha, and those will indicate the coordinates that I am interested in. And once in a while, I will use this notation. At the beginning, it will at least mean that it is negligibly small. It's just to highlight that a certain quantity is negligibly small. OK. So that's where we are. And remember, actually, we already considered two problems of plane stress and plane strain. So for plane stress, we had the thin spinning disk. Which we solved. And for plane strain, we had pressurized cylinder, the pressurized thick-walled cylinder. So we have actually already considered two problems that individually address these two simplifications. OK, so let's first recall what the assumptions are in these two settings. Okay. So on the left-hand side, we have the displacement components. And because it is a plane strain problem, I will, in that setting, only be concerned with displacements in the 1 and 2 directions, right, u alpha. And u3 is equal to 0, perfectly or nearly. Okay? So it's negligibly small or perfectly 0. Then we will have strain components, cis plane strain problem, u3 is 0, which means if it is 0, epsilon 3, anything will be 0. And all that remains is epsilon alpha beta, 1, 2, 2, 1, 2, 1, 2, 1, 1, and 2, 2. So, and all of these will always be a function of x1 and x2 only because variations along the x3 direction, they are omitted, right? So these are non-zero, and epsilon 3 anything is equal to 0. Right? On the right-hand side, for the plane stress setting, only the in-plane, so 1, 2, 1, 1, and 2, 2 components of the stress are are non-zero, and eventually sigma 3, anything, so sigma 3, 1, 2, 3, they are all nearly 0. And when we solve, we say that it is exactly equal to 0, but in reality, it is nearly 0. Okay, so those are the important assumptions. Now, immediately what I can do is I'm going to next talk about the material model. Okay, I'm going to talk about this equation and try to sort of play around with it a little bit. Before I do that, let me apply it. So this part is really something that we deduce from the material model, right? So when I look at the material model, linear isotropic elasticity, and look at these assumptions, now in the context of linear isotropic elasticity, I immediately see from this constraint, although I don't say anything directly for the stresses, I see that, for instance, here, epsilon 3, 1 is equal to, right? These components only go to the diagonal ones, right? So it's an identity. 1, 1, 2, 2, 3, 3 components are contributed to by sigma h. This has to do with shear, and this is 1 over 2 mu. You can also see it here. So for the shear component, sigma is equal to 2 mu, the shear strain. So epsilon 3, 1 is 1 over 2 mu, sigma 3, 1. And epsilon 3, 2 is 1 over 2 mu, sigma 3, 2. And since epsilon 3, 1 and 3, 2 are 0, I see that sigma 3, 1 and 3, 2 also have to be 0. Okay? So my assumption is regarding the strain, but at least for the shear strains that have to do with the third axis, the out-of-plane direction, essentially they're also 0. So on the other hand, if I look at the right-hand side, here my assumption concerns not the strain, but the stress. But here, similarly, I can see that since sigma 3, 1 is 2 mu epsilon 3, 1, and sigma 3, 2 is 2 mu epsilon 3, 2. And since sigma 3, 1 and 3, 2 are 0, I see that the two components of the out-of-plane strain, so epsilon 3, 1, and 2, they have to vanish. Okay? My assumption is concerning the stress, but those components automatically also vanish. So that's something that we deduced from the linear elasticity, isotropic linear elasticity relation. Okay? So let me examine that relation a little bit further. So the material model. So we start with the plane strain case. Epsilon 3, 1 and 3, 2 are 0. Epsilon 3, 3 is also 0. Sigma 3, 1 and 3, 2 are also 0, but sigma 3, 3 is not necessarily going to be 0. This we already know from that problem. Okay? In fact, due to the constraint that epsilon 3, 3 is 0, sigma 3, 3 will not be 0. So what is it? It's something that we would like to find out based on our isotropic linear elasticity relation. So I set epsilon 3, 3 is equal to 0, and I'm essentially following this relation. This for plane strain, that for plane stress, I'm going to examine. Right? So epsilon 3, 3 is equal to 0. It's minus 3 nu over E. Hydrostatic stress, which is sum of the diagonal components divided by 3. Okay. Plus 1 plus nu over E sigma 3, 3. So the 3's cancel. There is a minus nu over E sigma 3,3, nu over E sigma 3,3. They cancel. I'm only left with a 1 over E multiplying sigma 3,3 and a nu over E multiplying 1 on 1, 1 plus 2, 2. So sigma 3,3 therefore is equal to nu times sigma 1, 1 plus 2, 2. Okay. Again, as we actually already know. So since sigma 1, 1 and 2, 2 are quantities that only depend on x1 and x2, sigma 3, 3 therefore is a quantity that depends on x1 and x2. Okay. So on the other hand, I can go to plane stress. In the plane stress setting, sigma 3,3 is equal to 0, but epsilon 3,3 is not necessarily equal to 0. So sigma 3,3 is equal to lambda epsilon v, the volumetric strain, which is 1, 1 plus 2, 2 plus 3, 3 plus 2 mu epsilon 3,3. Or, therefore, you can solve for epsilon 3,3 equals minus lambda over lambda plus 2 mu epsilon 1, 1 plus 2, 2. Okay. Which also, in fact, is something that we've done before for the thin spinning disk. And since epsilon 1, 1 and 2, 2 are functions of x1 and x2, epsilon 3, 3 in this case, it's a function of x1 and x2. Okay. So these, I've already used the wording once or twice since now. I will call the out-of-plane variations. Because in-plane components that I'm interested in, or the in-plane coordinates, are x1 and x2, plane stress or plane strain. So the plane I'm talking about is parameterized by x1 and x2. So anything that has to do with 3, it's for me an out-of-plane component. And it's essentially going to be a byproduct of my solution. I don't solve for it directly. I solve eventually for 1, 1 and 2, 2 components. And the 3, 3 component is a byproduct. Everything else is 0, right? So in this case, for instance, 3, 1 and 3, 2 are 0. In that case, 3, 1 and 3, 2 are also 0. So how about the in-plane components? So for the in-plane components, let's observe the hydrostatic stress is eventually equal to sum of the, so the hydrostatic stress is 1, 1 plus 2, 2 plus 3, 3 over 3. But now I have 3, 3 expressed in terms of 1, 1 and 2, 2, right? So I can plug that expression in there. This is my sigma h. And that's sigma h. And that was, by the way, the volumetric strain. And I can have an expression for sigma h only in terms of 1, 1 and 2, 2 components. Okay? So by directly substituting that in there, I obtain an expression for sigma h in terms of 1, 1 and 2, 2. And here, I can obtain an expression for epsilon v by substituting this in there in terms of 1, 1 and 2, 2. Okay, so now what I'm going to do is, just to remind you, for plane stress, I'm going to plug in epsilon v there in terms of only 1, 1 and 2, 2. And for the plane strain case, I'm going to plug in sigma h only in terms of 1, 1 and 2, 2. And I'm going to get an expression respectively for epsilon alpha beta and here for sigma alpha beta. And those expressions are, after only a little bit of manipulation, okay. In fact, almost no manipulation. And these two eventually are the in-plane components of stress and strain that I'm interested in. Okay, so remember, the goal is to show that eventually both intrinsic problems, plane strain and plane stress, they can be cast in an identical framework. So if I want to cast things in an identical framework, I better be able to express the relation between strain and stress in also an identical manner. So this is a relation that gives strain in terms of stress. You can always invert it, right, as we've done before in order to go from, we started with that expression, and afterwards we obtained that by inverting, or we can go vice versa, right? So similarly, here now I have a relation. I can invert that and write sigma alpha beta in terms of epsilon alpha beta. And here I can invert this and write epsilon alpha beta in terms of sigma alpha beta. It turns out those two expressions are not the same. They cannot be the same. The physics, they're different, right? This is plane strain, that's plane stress, right? But functionally, we can cast them in an identical form. So now this part, I'm going to skip a little bit. I'm just going to write the final results. So let me call this sigma epsilon conversion, by which I mean that given epsilon in terms of sigma, now I want to write sigma in terms of epsilon, etc. So in both cases, for plane stress and strain, I mean, we have only two components appearing. And so, possibly, they can be functionally, at least, expressed in a similar fashion. I am skipping the details, right? So I encourage you to verify that these are correct by going ahead and showing that under suitable assumptions, plane strain or stress, that they're identical to those forms. So we can show that, for instance, in both cases, sigma alpha beta can be expressed as so now I'm introducing a new constant, omega. That's for sigma, and for epsilon, again, we have a quite similar form. And the new constant that I've introduced, it's here. This is the constant, right? So eventually the expressions will look different, but functionally they are the same if I introduce this constant omega. And this constant, if I'm talking about plane strain, takes the form 1 minus Poisson ratio. And for plane stress, it takes the form 1 over 1 plus Poisson ratio. Okay. So what you can verify is you can plug in here 1 minus nu and show that you have, for instance, that expression. What you can also verify is you can invert this expression as an exercise for sigma alpha beta and make sure that it is equal to this one again after you substitute omega equals 1 minus nu. These are just things to sort of experiment with these forms. Okay? But now I have a form that applies in principle to both plane stress and strain. Right? The constraints are in some sense different. Eventually, once you calculate everything, you know that for plane strain, epsilon 33 is 0, and you obtain sigma 33 like this. And for plane stress, sigma 33 is 0, and you obtain epsilon 33 like this. But aside from that, in terms of the in-plane components, things look generic, okay? Which in fact implies eventually that when I solve my problem, I don't need to, from the outset, impose the fact that I have either plane stress or strain. I can just retain a generic form, And at the end of the solution, I can choose whether the problem was plane stress or strain. That will give us some flexibility. That's what I mean by eventually a unified framework. But let's proceed further. Okay? Eventually, my goal is twofold: to show that we have a unified framework for plane stress and strain. And the second one is, remember, I am trying to go for a stress-based solution. So eventually, my goal is also to show how this type of a unified setting eventually condenses or is employed in a stress-based solution approach. OK, so we have the strains, we have the stresses, and of course, what comes next is a consideration of equilibrium. Okay, so let us do that over here. Now, equilibrium has little complication with respect to the particular setting we're looking at. So it looks identical for plane stress or strain, because it is in terms of stress after all. Oops. OK, so in these problems that eventually we will solve in a stress-based setting, I will assume that there are no accelerations. Remember, there could be an acceleration. For instance, in the setting of the plane stress problem of thin spinning disk, there was an acceleration. It was a radial acceleration. And I could alternatively interpret it as being a body force in the radial direction. So the fact that I'm saying u double dot is equal to 0 does not mean that I cannot somehow squeeze in some sort of acceleration effect into the problem. I can, okay? And I can do that through the body force. So we are going to assume that the body force per unit volume has only in-plane components. So F3 is equal to 0. And in Cartesian coordinates, and let me highlight just once again that everything that I'm going to do involving differential operations, they are going to assume Cartesian coordinates, but eventually the final results are independent of whether it is Cartesian or any other coordinate system. So let's just highlight that for a second. So in Cartesian coordinates, I know that the equilibrium equation in the one direction, sigma 1, 1, comma 1, 1, 2, comma 2 plus F1 is supposed to be equal to 0. And in the two directions, sigma 2, 1, comma 1 plus 2, 2, comma 2 plus F2 is also equal to 0. And I'm going to call this equation number 1. I will refer to it shortly. And the second one as 2. So that's my equilibrium, nothing fancy. And then we have compatibility. So these pertain to both problems, right? Plane stress or strain. And now we have compatibility that we also need to consider, right? This is pretty much the last piece of important information missing, right? In order to solve our problem. So compatibility. We do have a intrinsically 2D setting, and you might remember from our earlier comments that there is only one relevant equation remaining. There are 6 compatibility equations, but almost all of them involve 3 components, out-of-plane components, and the one that eventually survives is one that I had boxed among those 6 equations when I was talking about compatibility, and it's this one. Okay. Again, nothing to memorize, of course. Let's call that equation star because, again, I will refer to it. So now there is a bit of an important point. So in a plane strain setting, this is perfectly sufficient. There is no additional simplification involved. In the context of plane strain, this is indeed the only relevant compatibility equation. Everything else identically vanishes. Now, for the plane stress case, there is something we need to be careful about a little bit, and I will call this the first item that I want to remark on shortly, but I will do that in a few minutes, not immediately. Okay? So I'm going to add a remark there. So that is the compatibility equation in terms of strain. Okay? It makes sense to cast it in terms of strain because eventually, if the strain satisfies compatibility, then I will try to construct displacement from the strain. But now I'm going towards a stress-based approach. In the stress-based approach, the variable that I have describes the stress. Now, once I have the stress, I can go and always write the strain like this. Plane stress or strain doesn't matter. Now, instead of writing compatibility in terms of strain, I would like to write it in terms of stress because that's what I will be working in terms of. Okay? So in principle, all you have to do is take this expression and plug it in there. Okay? And if there are simplifications, work it out. And if you do that, okay, and this is the second remark that I will make. I will show you this derivation. So this is our second remark that we would like to dwell on a little bit. You can show that the compatibility can also be written in terms of stress, and the expression is the following. Right? The constant omega remembers. It's defined individually for plane stress and strain. Right? The expression itself is irrespective of whether, so functionally it holds for both settings. Once I pick a particular value for omega, then it becomes specifically plane stress or strain. Okay, so now I'm pretty much done with the basics. So I've shown you that plane stress and strain problems are cast in a unified setting, but eventually we want to work towards a stress-based approach. The stress-based approach works in an intrinsically 2D setting. Eventually, it doesn't matter whether it's plane stress or strain. The equations we'll be using are identical, at least functionally, right? The only free parameter, let me say, is omega. Okay, so those two remarks are the two things that I'd like to spend a little bit of time now. So let's begin with remark number one. So first of all, for plane stress, the problem is not for plane strain. For plane strain, the compatibility requirement is perfectly satisfied. But for plane stress, what we have is epsilon 3,3. It's not equal to 0, but it is a function of 1 and 2. For plane strain, it is equal to 0, and therefore that's why all the remaining, along with 3,1 and 3,2 components, all the remaining components or equations of compatibility are things we don't have to worry about. But for plane stress, this is not 0, and hence, we also need to satisfy actually 3 more equations where epsilon 3,3 somehow remains. And those equations are these. Please go back to the discussion of compatibility and see that these are indeed the 3 components which remain. So verify that. Okay. So that's what we essentially have remaining. Now, this last one is particularly straightforward because it tells us that epsilon 3,3, 1 to 0 means that epsilon 3,3 is at most a linear somehow function of 1 and 2. There could be some small complications perhaps, but aside from that, epsilon 3 x1 and 2 due to these things is highly restricted. And remember, right, so these are restrictions on epsilon 3,3. And remember that epsilon 3,3 is eventually equal to epsilon 1,1 plus 2,2 multiplied by that material constant, which therefore is a restriction on the displacement components, U1 and U2. Now, it turns out that this restriction can be so severe that if we try to impose it from the outset, it's almost as though I'm going for an exact solution. So it's qualitatively, not quantitatively, or in fact, even qualitatively, it's a little bit forcing the analogy. But remember the simple problem of a cylinder under tensile force, right? There we had the end effect, and eventually we, in view of the Saint-Venant's principle, we omitted the end effect. If we don't omit the end effect, we have a complicated solution. It's something that we cannot easily solve for. It can be solved for in some instances. However, if we omit it, then we have a very simple solution. So it's a similar situation here. Perhaps it is possible if you strictly enforce it, but it turns out that it's often so severe that it is better to omit it. And if you omit it, then your life becomes essentially much simpler. So we are going to eventually not satisfy these three compatibility requirements for plane stress. And those quantities or those requirements have to do with the out-of-plane component. For the in-plane components, everything is perfect. This is the requirement, and we will satisfy it. But eventually, we will be making a small error that has to do with epsilon 3,3, and perhaps eventually with that has to do with U3. But also, U3 is something that we're not going to solve for. So this is an error that we will have to live with. That is the first remark. So it's an approximation. Take it as if you like, to be something similar to omitting end effects. Okay? It is an approximation. It's a reasonable approximation. We could perhaps not do it, but then our life certainly would become more complicated. So we are going to go for an approximate solution, therefore, right? Just like when we omit end effects, we also obtain an approximate solution, which just happens to be a very good approximate solution. So that is sort of the hand-waving part. So we believe and hope that indeed our assumption is reasonable. The second part is a derivation. Now, I'd like to move on to starting from here, using the relation between stress and strain, and writing the compatibility in terms of the stress, okay? Because that's what we need in a stress-based approach. So let's do that. Okay. So that's item number 2. So what I will do is I have erased these expressions, but in terms of omega, I'd like to express epsilon 1,1, 2,2, and 1,2 in terms of stress first. Okay? In a way that it holds for both plane stress and strain. So let's start with the 1,1 component. So I had epsilon alpha beta, 1 over 2 mu sigma alpha beta, minus 1 minus omega, that multiplying delta alpha beta. In this case, I'm looking at the 1,1 component. Delta alpha beta is 1. So that term is retained. So similarly, epsilon 2,2, 1 over 2 mu sigma 2,2 minus omega, sigma 1,1 plus 2,2. And finally, we have epsilon 1,2, which is always easy, 1 over 2 mu sigma 1,2. The first two we can simplify a little bit further because there's a sigma 1,1 and there's a minus sigma 1,1. So with that small simplification, these are what we end up with. Okay, so now I take these and plug them in there. Okay, and I'm going to rewrite this equation star. So let's begin with epsilon 1, 1, the first component. So the 1 over 2 mu factor appears in all of them. Eventually, this thing is equal to 0. So I'll get rid of that 1 over 2 mu factor from the outset and immediately go for what are in the brackets. So omega sigma 1, 1. In the first term, I have a comma 2, 2. So I'm going to move that in here, comma 2, 2. Minus 1 minus omega sigma 2, 2, comma 2, 2. So that's the first term, incompatibility in terms of strain. The second one, epsilon 2, 2, comma 1. So omega sigma 2, 2, comma 1, 1 minus 1 minus omega sigma 1, 1, comma 1, 1. And that's it. And then minus 2 multiplying sigma 1, 2, comma 1, 2. And that has to be equal to 0. Okay, so now this is in principle the compatibility in terms of stress, right? But I have already mentioned that in our loop, the solution diagram in a stress-based approach is not a complete loop. It starts from the stress, goes towards the displacement. There was an equilibrium equation up here that we did not really use. So it needs to be satisfied from the outset. So stress, it turns out, does satisfy, will have to satisfy from the outset. And since it is satisfied, it turns out using equation 1 and 2, I can simplify this expression a little bit. So let's also do that. Okay, so also since equilibrium is, or let's say will be, satisfied from the outset. So let me go. And what I'm going to try and do is so I have, you see, a 1, 2, comma 1, 2 component, right? I'm going to try and get rid of this component. Okay? Eventually, my equilibrium equation only will be in terms of 1, 1, and 2, 2. It just looks nicer that way, and you will see why it looks nicer that way. So to get rid of this, for instance, I look here. There's a 1, 2, comma 2. If I take a derivative with respect to 1, then I will get the term that I need from the first one. And also, if I look at the second one, if I take a derivative of this with respect to 2, again, I will get a term that looks like this. So that's the motivation for the next two steps I'm taking. I'm trying to get this term from that and that equation individually. So for the first one, as I said, the way to do that is take another derivative with respect to 1. So in that case, I get sigma 1, 1, comma 1, 1 plus sigma 1, 2, comma 2, 1, right? Now I have that term, plus f1, comma 1 is equal to 0 from the first equation. It has to be that way. And from the second one, sigma 2, 1, comma 1 is what I have. So if I go ahead and take a derivative with respect to 2, I have the term that I desire. So then 2, 2, comma 2, 2 plus f2, comma 2. And from the second part of equilibrium, I have that equals 0 as well. So This is equal to minus that plus that. That is equal to minus that plus that. So if I isolate these two terms and then eventually sum up these two, right, I obtain minus 2 sigma 1, 2, comma 1, 2 is equal to that plus these two. Okay. Okay. So now the only thing that remains is to take this actually the whole thing and substitute. And there is a single line remaining. You can complete that on your own. Once you substitute and you rearrange, then you will obtain eventually that equation. Okay, I just paused for a second because I thought I made a mistake, but then I look, okay, everything is fine. Okay, so once you substitute, then you will get that result. All right, so we're done. Okay, so now essentially two things need to be highlighted here, and let me write that in a different color to emphasize that. The first one is that as I took this step, I assume that equilibrium is satisfied, which means that when I write this equation, I am assuming equilibrium is satisfied. We will satisfy it. It's not a problem. That's one thing we need to be careful about. Two, I am assuming a particular relation between stress and strain, isotropic linear elasticity, which also needs to be satisfied. So although this compatibility requirement is irrespective of what type of a material model we're looking at or whether or not equilibrium is satisfied, this one is a more restrictive form, but that's the one that we are going to use. So the things we need to highlight here is that equilibrium must be satisfied, and isotropic linear elasticity must hold. So the compatibility in terms of stress is a little bit more specific form. Okay, so we're pretty much done. So now I have everything in my hands that I need to proceed with a stress-based approach. And we're going to start with the heart of it next time. Okay? And I think in one lecture we will see the major features of it. Okay? So that's all for today. I'll see you next week.